So this is a 6-node cluster running in our data center, and these nodes are basically standard white box servers. In this case, they are Supermicro, right? They have about 24 drives apiece. That includes a couple of SSDs, right? And dual socket processors. And these nodes are basically runs a couple of services, the data and the metadata part of the service, right? And every node you can connect to the UI. I'm connected to one of those nodes. The same, I could connect to any one of the nodes to get this UI. In addition to the data and metadata, there is basically about 2 or 3 compute nodes, in this case VMware ESX, on which there are controller VMs running, which expose storage from the cluster to the hypervisors, right? So you can go, basically, you can, so the gateway to the cluster is basically these nodes expose NFS or block devices to the hypervisor or to individual clients. You can mount them and consume them as block devices or as NFS. Okay, so I'm just going to go through an exercise to show you how easy it is to create a virtual disk and expose and format it as in a Linux environment, and show the same on a VMware environment, right? And then we go through some of the snapshot and clone capabilities that are built into the system from day one. So to basically create a disk, you just go in here, and I'm going to carve out a disk. Just give it a name, and just create it as 10 gigabytes in size. And the disk type here can be block or NFS. And these are some flags that that you would have to set if you were, for example, exposing the disk as an RDM LAN, as an RDM device to ESX. You can check options for deduplication, or for, like, if you were to use a clustered file system on top of this, such as say VMFS, right? We need to know that. Then there are options for client-side caching and compression that you would turn on. The replication policy, in this case, there are 3 possibilities: data center aware, agnostic, or rack aware. Right? So the replication policy is determined by the nodes in the system, and the node names we allow you to configure the node names in such a way that you can give a parameter which tells you from the node name if a data center is present in the name. We can use that to then keep your virtual disk on located on the nodes per this policy. The residence of the disk can also be selected as hard drive or flash, and then this is the replication factor for this disk. I'm just going to go create, and I created this disk called demo01. The details of which is the same here, right? I basically created with an agnostic policy with the residence hard disk. And then there are 2 things here which basically talk about the block size and the exporter block size. This is like your sector size on your media, right? So if you bought a new disk nowadays, you would get a 4K disk with 512 emulation. This particular disk here doesn't have emulation, but I can turn that on if I need to, right?
Do you guys do any sort of tiering, or do I have to specify, because you pin that disk to a specific media?
Yeah,
so,
the disk, yeah, go ahead.
Sorry. So just to map this to what I scribbled over here, right? If you see that disk residence, that is what is pinned to flash or pinned to hard disk drives, right? There is auto tiering support that is implicitly enabled on the storage cluster. So if you have SSDs there, hot data automatically migrates into the SSDs and migrates off. Cold data migrates
So you
off.
can pin it one place or the other, or if I don't, it will
automatically do it for you.
Okay,
So pinning gives you this explicit control over where you want data to be. That's why when I put this down here, I said if one wants dedicated, consistent performance, then you do that.
Because if I was a storage admin, that UI would confuse me, because it would look like I had to pick one or the other.
No, I understand. No, I understand.
So moving along. So once I've created this disk, I'm going to expose this, in this case as a block device. I'm going to expose it as an iSCSI LUN. And I'm going to just select a controller here. And once I've done that, I'm going to give access to an initiator. I'm going to change my screen to be, you'll see a CLI window here. Sorry. And this is the client to which I gave access. Now if I scan the iSCSI LUN, I've got a device here, the device I just created, SDC, which I'm going to just format and create a file system on this.
So the key here being that you're creating these virtual disks in a system that's very modern, but it presents itself as if it were a locally attached SCSI disk at the end of the day. Right? So the usual workflow naturally fits in.
And I've got this device, SDC, which is the same as my disk over here, demo 01, right, in here, and it's implicitly, again, it's redundant underneath the surface, right? It's distributed according to the policies of the replication policy I originally selected.
Quick question, if you don't mind. Do you have to drop out of the GUI to come to the CLI to do this, or is this something that's handled in the GUI as well?
Well, it's like if you were a storage admin and you expose a LUN, then the control of that LUN passes over to the user who needs to format the LUN with a certain file system, right? So right now, this is an app. For example, in this case, this machine is a part of Hedvig, but you could be a storage node and then exposing the LUN to some customer's environment, and that's where you would be formatting and mounting it from. So that's why this part you cannot do through the GUI, because the control of that screen is not available to you.
Okay, thank you.
So this is a typical kind of sysadmin functionality using existing tools that are on a Unix platform, right? So what we have done here is, it's a modern system, but you can use the same operational steps to achieve what you want. You're not changing the operations that people have been used to doing for the last 10-15 years.
So now the other thing that I wanted to show you here is that snapshot and clone is built into the system. So I can go to this disk and do new snapshot, right? And for us, snapshot is just a metadata update. Regardless of the size of the disk, the snapshot is blazingly fast. Once I've created a snapshot, I can go clone this and create a new disk. Now it's important to note this new disk does not have to live on the same media or on the same servers as the original disk, right? Like, say for example, you have the original disk, which was demo 1, which resided on, say, a certain set of servers. There is the new clone will not necessarily live on the same set of servers.
So let me give you guys 2 real-world examples of why this is very powerful, especially the way we do things. If this were a database that's running in production, and let's say the disk residence was SSD, right? Developers always need a test environment, and hopefully if it looks and feels like a production environment, the chances of you flushing out bugs are greater, right? So what you could then do is snapshot this virtual disk, just the way Suresh did it right now, and then you can create a clone of that virtual disk and make that the test environment. So now test and dev are not stepping over each other's toes, and you can get the full production-like environment available in your test environment, right? That's one way people are using it. The other way, which is even more interesting, which we unfortunately cannot show in this demo, is that there are customers who create these virtual disks replicated across data centers like this. And for business reasons, they need to sometimes switch over and have this replicated on a totally different set of data centers, right? So what they do again, they snapshot and they clone, and when they clone, they can change the policies. So they'll change these policies on the clone to be perhaps DEF, and then present that as a volume or an NFS mount point, and things work seamlessly for the application.
So moving along, I'm going to just create this clone, and the clone, I'm just going to expose it again as a LUN. And then give access to the same place. And just scan my session again. And I've got this device SDD, which was my clone. And that's the disk I originally formatted. Right. Any questions so far? Now the same thing we can do. We have similarly, I've got a ESX box here. This machine where I can create a LUN, right, and either mount it as a block device or as a NFS share. So let me show you that here. So I'm creating an NFS disk here, and once again, the NFS disk, I'm just going to now expose it, which basically means that create a share. We first went through the process of creating, just carving out the space of the 2 terabytes. Now we're just going to expose this share. And on the ESX box here, we're going to mount this share. And this share is being mounted from the controller VM that is running on that same ESX where we exported it to. And that's the disk I just created, right, 2 terabyte, and can be consumed by any of the hypervisors to run your VM or put database on it or what have you.
So that's the share on which your VMDKs go.
Right. We also have integration with OpenStack. And this is an OpenStack environment running against this Hedvig cluster, right? So what we have also done is we have a cinder driver which integrates with OpenStack, so that when you go through the normal OpenStack interface and you create volumes, those volumes use the cinder driver to create to provision the storage on Hedvig.
So just to highlight something,
Yeah.
The cinder driver, again, is invoking APIs that we expose. Now, it's the same APIs that we are also invoking from the user interface that we provided. Same APIs that one could script against if you so choose to do so. Right? So everything is API driven, from management to being able to program against the system to get data in.
So let me go through the create volume. So I can create a volume called and then again here I can choose whether this volume should be based on a block or NFS device. Just go through create volume. Now I should add that all the operations that we are doing through the web interface or through what we have a CLI are also available through a REST interface. So you can program all of these commands and provision all of your storage through REST API. I can then, once I've created this volume, I can attach this volume to an instance. And I've attached this volume to an instance available to use there. In this, in this OpenStack, there is also we have replaced the object store component with our object store, right? So if you were to use Hedvig with OpenStack, when you create object store for containers or upload objects, those use our object API to create these containers and objects on Hedvig. So I'm going to go through this exercise here, which is basically effectively we are Swift compatible here. So I'm going to go through a create container. And in this thing, and I'm going to go here, upload object, choose a file, so this is through the Swift interface of the system, the same system that can store objects, that can expose objects as, that can expose a block device, a vdisk as a block device, or as a NFS, can now also expose a vdisk as a object store device.
So if you were to get the parlance for Swift, I think it's called a container. And to get the parlance right, for Swift, it's called a container, and for S3, it's called a bucket. So now in this world, a virtual disk will map to an S3 bucket or to a Swift container based on which API you kind of decide to kind of program against the system. Right? But the key point here being that, you know, it's one platform and you can use all these storage protocols almost seamlessly, right?
So the last thing I wanted to go over was the S3 part. So I'm just going to change my screen to a AWS CLI like interface. So I'm going to create a the system exposes a S3-like interface. So just created a bucket, right? And then now I'm just going to upload something into this bucket. Uploaded this into the bucket. I can copy it back if I want to do. But you get the idea. Downloading. So in effect, the system can, like I said, is compatible with a S3 interface. You can speak to the system through an S3 interface. You can speak to it through NFS or block. You can start with, in this case, 6-node cluster, right? You can add nodes. You can scale the cluster, right? As your storage needs grow.
And if you guys remember, I said that we track a lot of metadata and we do a lot of intelligent things internally within the system, and you can visualize all that. For instance, if you were to go into this node, right, what you see over here are what are called how we manage the JBODs, right? So what we do is, if you have n number of JBODs, we group triplets and deem that a storage pool, and we manage that. And when I think you had mentioned, we carve it into 30 slices and spread them over.
Right.
In fact, there is a term for that internally, which we call containers. And when you assign a container to a particular server, within that server it gets assigned to a storage pool, and we even track visually, because this is all metadata that we store in the system. So you can actually look at this and figure out what container it is, and it will tell you what's the name of that container. You can figure out which vdisk that relates to, right? All this information is available, right? And that's what we mean by completely tracking every piece of information within the system. There's also stuff that we have which may not make a lot of sense for the normal user, but
does it also return this sort of granular information when it's running as a VM in a cloud service?
Yes.
Such as Hyper-V, Azure.
We have not tried anything on Azure yet, right. But on AWS, yes, you can get the same information.
Okay.
Right? So you can actually track, this is for that particular virtual disk, where the containers are placed within the physical cluster, right? You can see that container 1 is on nodes 11, 10, and 12, and stuff like that. So every piece of detailed information is available for one if they really want to take a look at it, right? So it's a very rich system with a lot of metadata in there. What we plan to do going forward in the future is build an ecosystem around it so that we can preemptively make recommendations to customers based on things like, we should be able to tell folk, in cluster ABC in your environment, in node 10.1.2.3 in this particular storage pool, this disk is probably going bad. You may want to replace it, right? Because we have all that information, we can beacon that out to a central repository that we can track, right?
Sorry, how would you tell it might be going bad? You have metadata that will tell you how it might be going down?
Yes, like typical ways of doing it is tracking latencies and stuff like that, right?
Okay.
And then you can use smart metrics that are readily available in Linux and keep them monitoring that over time.
That's something you can demo?
We don't have it today.
Oh, okay. So you're going to have it.
My point is, the metadata is so rich that you could take that metadata and make and run deep analytics on top of it to make such recommendations. But the first step towards getting there is to actually have that data, right?
And that metadata can be exported to any sort of BI
analytical tools.
Analytical tool that can.
Yeah, you can query against it if you want.
Query right against. And how is it stored? I'm sorry if I missed that before.
It's stored in a proprietary format, but we expose APIs for you to go and get it out.
Okay.
So it's all API driven. That's what I meant by, everything is API driven.
Okay.
And to get to the question that you were posing, before I get into that, I wanted to mention some of the things that we do where, the different ways in which we leverage SSDs for accelerating performance, right? In the system, there are 3 particular ways in which you could do it. So if you guys remember that slide that we had, there was this Hedvig cluster sitting there, and then you had your entire compute tier over here, right down. This could be any hypervisor. We don't really care. Now, nowadays, almost every compute environment comes with PCIe devices or SSDs in them, right? So what you could do and this is our Hedvig storage proxy, right? If you have local SSDs or PCIe devices, then for certain virtual disk, there is an option that you could choose where you could say, do client-side caching, which basically means that the storage proxy can leverage those SSDs to cache locally on SSDs. So if your entire hot set fits over there, then you will be literally rendering the data to the application at local SSD speeds, right? These are kind of things that you could leverage with this platform, right? In addition to doing auto tiering over here, or pinning virtual disks to flash. Right, so the system is very, very flexible that way in terms of lending itself to the applications that are latency sensitive. Right? And to answer your question about what kind of applications are people running, and you in particular brought reference to a financial organization, which we are working with. So some of the things, the reason why they're going with us is, one, the simplicity to kind of provision and to use the system, right? They are currently running us across 4 different data center locations, right? So the ability to have cross data center replication kind of built in was a big plus for them, right? This complete protocol consolidation was a big deal for them because they were using block, they were going with a particular vendor for block, another vendor for NAS, and trying to figure out what their object storage strategy should be, right? For us, when they come with us, it's all bundled into one platform, like just the way you saw it, right? Some of the things that they are doing, which really is, moving the needle for them from an application standpoint, apart from the simplicity in provisioning, is the ability to change certain properties based on business requirements, like the ones that I mentioned. How do you change the data center replication set almost on demand, right? It's not, I would be lying if I said it can happen in runtime, but it's almost on demand. You could achieve that. These were all kind of fundamental pain points that they wanted addressed, right? Apart from that, of course, the cost. The cost, CapEx, we don't even have to talk about because this runs on off-the-shelf commodity hardware, right? But operationally, we can reduce the burden pretty significantly, right? Provisioning storage assets, these guys already have scripts written around our APIs, and they're up and running with all those. So the simplicity was the main driving factor.
Why did you target ARM processors at the start? Did you think there was there's an opportunity there? Do you still see an opportunity in supporting ARM? Oh,
no, it's not. So here is why, right? I mean, some of the thinking has to be forward-looking in nature, right? Now, ARM64 is not prevalent yet, right? But let's assume that we are now at a point where ARM64 is readily available, right? Now, the problem that people always talk about ARM, I mean, it solves one big problem, which is power, right? But the one that holds people against mass deployment is performance, right? Now, what if you could do ARM and flash? That can be a very potent combination. Why? Because if you look at what are the 3 big components in a data center that consume a lot of power, it's CPU and disk, right? Yeah. 2 of them, actually. Now, the CPU problem can be solved if you move to ARM, but the disk problem still exists, right? Now, flash kind of lends itself to solving that problem. So ARM and flash, you can alleviate some of the performance concerns and get total bang for the buck if it truly delivers, right? Now, if your software is capable of leveraging that, that's really great.
And actually, let me...
Technically, yes, it looks like, but and you're probably closer to this than I am. Actually, you are. Do you see ARM processors, even ARM64, having the headroom to carry enterprise workloads outside of web scale workloads? Because I don't.
We don't know
What
that.
I see.
We don't know that yet. We have done only basic experiments. The point that we're trying to make is, I think it will get there because all the big boys, including AWS, are investing heavily in it. So it will get there.